All right, welcome back. So let me continue from where I was. So this is our example dynamical system. Now, clearly, one thing, the first thing we're going to look at is the steady state. So let me reserve some space here. So these parameter values will be important, but I want to keep the system here. Okay. So for steady state, we are looking at PT plus 1 equals PT equals P, right, or P star, and AT plus 1 equals AT equals A, all right? So if you do the math, you see something like this. So P equals, from the first equation, beta A to the alpha, P to the C minus delta P. So this implies 1 plus delta P 1 plus C, right? Beta A to the alpha. So from this, you see there's a relationship between P and A, right? So you have beta A to the alpha divided by 1 plus delta 1 over 1 plus C, okay? And from the second equation, you have A equals gamma A theta P lambda, right? This implies P lambda is equal to A 1 minus theta divided by gamma, right? So you have P equals A 1 minus theta gamma to the 1 over lambda, right? Now, obviously, if you equate these two equations, these are two equations and two unknowns, then you find a particular A star, okay, or A, then you put this either into here or here, and you find P star, okay? So in this problem, as long as these numbers are not magically implying linearity or zero, you will have a unique steady state. Then you may want to ask about the stability, and for this, you're going to draw a phase diagram. Okay? So in the phase diagram, we want to find a PP locus, right, and an AA locus. So the PP locus will be formally a set, okay? So we can denote it as PP. So it will be a set, and this set will be a set of points in two-dimensional space, P and A points, right? And these points will satisfy PT plus 1 equals PT, all right? And for the AA locus, we will have, again, PA points where AT plus 1 equals 80, right? So, so in the P equation, we have beta AT alpha PT Psi, I guess, right? Is that Psi? So you have that. Then, if you equate this to PT, so you have something like this. PT equals beta AT alpha PT Psi minus delta PT, right? Then similarly, you have beta AT alpha equals 1 plus delta PT 1 plus psi, right? So AT then as a function of P, AT is something like this, PT 1 plus psi divided by beta to the 1 over alpha, right? So you have something like this. This is PT and this is AT, right? So you have, depending, so this is the exponent, right? So you have so you have something like this, okay? This is your PP locus, right? Because these are so along this curve, along this locus, PT plus 1 is always equal to PT. Okay. Then you of course ask how can P change here and here, right? Remember, we took some derivatives and we find the streamlines. We find the movement of the system in these points. Now here, you're going to look at the sign of this. You're going to look at the sign of this, right? If this is negative, then P is decreasing. If this is positive, P is increasing, all right? So you want to look at the derivative of this with respect to, let's say, A. Okay? With respect to A. So how do you do that? Well, once again, you write your system. It is beta AT alpha PT psi minus delta PT, right? Then you look at PT plus 1 minus PT. So it is basically beta AT alpha PT psi minus delta PT minus PT, right? And if you look at this derivative, okay, if you look at this derivative, it is positive, right? It is positive. So if A is increasing, first it must be negative, then 0, then positive, because it is always increasing, right? Look at this. For positive population levels, it is always increasing. So your curve was like this, PT, AT, right? And this was your PP curve. Then in this direction, it is minus and positive. Okay? In this direction, look at the direction, right? In this direction, when A is increasing, first it is negative, then it is positive. So then P is decreasing in this region and increasing in this region. Okay? Careful, you are looking at how this difference change. All right? So next, we have the AA locus. So your equation was like this, if I remember. So it is AT to the theta, right? So this is theta, right? Just to make sure. And this is lambda, I suppose. Is that correct? Friends?
Yes.
Okay, theta and lambda. So then you look at this difference, AT plus 1 minus AT. So it is gamma AT theta PT lambda. All right. Oh, sorry. First, we're going to look at the curve. We're going to first look at the locus. So this locus will be defined in this way. AT plus 1 equals AT. So you have AT equals gamma AT theta PT lambda. So you have AT 1 minus theta equals gamma PT lambda, right? Then you have AT equals gamma PT lambda to the power of 1 over 1 minus theta, right? So if you want to draw it, again, PT is on the horizontal axis, AT is on the vertical axis. So this is lambda 1 minus theta. So this could be greater than 1 or less than 1. So suppose that it is less than 1, okay? So this becomes your AA locus, right? So then what happens? Then you look at this derivative, right? Derivative of this with respect to, and in this case, it is easier for both, but let's look at P, all right? So that derivative is also positive, right? Because gamma is positive, AT is always positive, PT is positive. So then in this direction, it must be negative first, then 0, then positive. All right, so it must be negative first, then 0, then positive. All right, so A must be decreasing here and increasing here. Okay. So if you want to, if you merge these two graphs, if you merge these two graphs, you have this, right? So you have the PP locus, so this is PT, and this is AT, and you have the AA locus. Okay, so you have where is it? You have AA locus. So for P, so now we have 4 regions, right? Region 1, region 2, region 3, region 4. So for A, we will be minus positive. So for A, it will be minus positive. And for P, it will be positive negative. So it will be positive negative. All right. So above the PP line, P should be increasing. Okay. And below the PP line, P should be decreasing. Now, above the AA curve, A should be decreasing. Okay. And below the AA curve, A should be increasing. Okay. Now, as you see, it looks a lot like stable node, right? It looks a lot like stable node. Okay. So this is how you do it if you want to look at the global dynamics, right? Remember the trade-off here. If you work directly with the nonlinear system, what you tell me in terms of the phase diagram is true for everywhere, right? So in here, in here, in here, in here, in here, it is always in this direction. Okay? But we don't know exactly how it will be dominated. Okay? I mean, here, we understand it from the graph, but if it was a spiral, we couldn't tell it, right? Then if you linearize the model, then you can tell me something more specific because now you linearize it, and then you can tell me exactly what is the type of the steady state, but then it will be true only around here. Okay? So that was the main trade-off, and that trade-off will also be applicable to discrete time dynamical systems. Okay? So that was just one example. Any questions about the methodology here? It's very simple. It's the same logic. We just look at the derivative to understand these streamlines, where is the movement of the system out of the steady state. We look at the derivative of the differences. Okay, we want to understand the sign of these differences. If PT plus 1 minus PT is positive, this means population is increasing. If PT plus 1 minus PT is negative, then this means population is decreasing. Okay. Now I will have a couple more examples if you have no question. Okay. So let's look at another example. We can write a very simple consumption wealth problem. Okay, suppose that this is your constraint. So so W here is wealth, and C here is consumption. Okay, so so in this problem, this is your transition equation basically, right? So gamma is positive, alpha is typically between 0 and 1. All right. So you may look at this equation in this way as well. Okay. So you have your asset income. Okay. Asset income. You may decompose this asset income into R and WT, and you may assume that RT is proportional to, RT, for instance, is gamma divided by WT 1 minus alpha. Okay? Right? So then RT times WT would be this. You know that. Then we also specify a function for consumption. Okay? And again, this is totally arbitrary. Let's say I have this. Okay, so this tells you that for positive consumption, if WT is greater than some level, not necessarily theta here, but it's basically equal to 1 plus theta. So increasing your wealth, if you have a larger wealth stock at T, larger than a particular threshold, you increase your consumption. If it is lower than that, you decrease your consumption. Okay? And here, you may assume that theta is positive. Okay? So steady state is very simple to find, right? Because by definition, we have, let me use a different color. So by definition, we have this must be equal to that, and this must be equal to that, and assume that we are looking at a positive steady state, right? Because that's the meaningful, non-trivial steady state. So in the second equation, you would clearly realize that C equals C times W minus theta. So this implies W minus theta is equal to 1. So W is equal to 1 plus theta, which is positive, right? Then in the first equation, you have W equals gamma W alpha minus C. So from this, C is equal to gamma W alpha minus W, right? So you have gamma times 1 plus theta alpha minus 1 plus theta. Okay? And of course, assume that if gamma is sufficiently large, then this is positive, right? So that's the steady state. Now, once again, we want to understand the stability of the system. And again, there is only one steady state here, one non-trivial steady state, at least. So we want to draw the phase diagram then. So let me write the system here once again. We have WT plus 1 equals gamma WT alpha minus CT, and we have CT plus 1 equals CT WT minus theta. Okay. Now the WD, this locus is again defined by WC points such that WT plus 1 equals WT, and CC locus is defined by WC pairs where CT plus 1 equals CT. All right. So for the first one, we have WT equals gamma WT alpha minus CT. In other words, we have CT equals gamma WT alpha minus WT. So you have, if you draw it, you have this. Okay, so this is your WW looks. Okay, and for CC, you're gonna have CT equals. Let me use the black. So you have CT equals CT WT theta. Again, you have 1 equals WT theta. Then you have WT equals 1 plus theta. So if you want to draw it, you have this as your CC logs, right? And this is equal to 1 plus theta. Okay. So then you can simply look at the derivatives. Okay. Let me use green for that purpose. So you want to look at, okay, just a sec. So you want to look at this derivative of WT plus 1 minus WT with respect to, as you see, it is simpler for C. Okay. And it is equal to -1, so negative. So in this direction, this is the CT's direction, must be decreasing. Okay, so in this direction, it will be plus 0 and minus. Okay. And for CC dynamics, you will have the derivative of CT plus 1 minus CT with respect to when, I mean, how it is easier? It is easier if you look at WT, right? And it is always positive, right? Because we look at positive C, right? So in this direction then, when WT is increasing, we have an increasing CT plus 1 minus CT, right? So if it is increasing, it will be minus 0 and positive. So it will be minus 0 positive. Okay. So then you can, of course, merge these two figures. Let me use here. So I have this, and then I have minus and plus. So what do I have? On the right of the blue curve, C is increasing, right? On the left of the blue curve, blue line, C is decreasing. Below the red line, below the red curve, wealth is increasing. Okay, and above the red curve, wealth is decreasing. Now, as you see, it's a spiral, right? Let me use this area for a zoomed version. So you have this, and let's say this, okay? You have this movement here, okay? You have this movement here. Then you have this movement here. And you have this movement here. Okay? As you see, it's a spiral. But now I cannot tell whether it is stable or not, right? Because we have two types of stable. It could be unstable or it could be stable. To understand that, I have to linearize. I have to linearize that. Okay, and then I already have that. So I look at the eigenvalues. And I will show you that next week, but that's the idea. So the global dynamics are spiral. Okay? And this is how you find it. Don't forget. So these are the things that you look at, all right? These differences, because you want to understand again the sign of this. Okay, you want to understand the sign of this, and you know exactly the sign is positive, sign is 0 exactly on this curve. The sign is 0 exactly on this curve. Okay. So that was another example. Anything you want to ask?
So what was the difference between optimal control theory and discrete time theory? In my understanding, optimal control theory, in the optimal control theory, we look at the whole system until the positive infinity or some t. But in this discrete time theory, we look at the between t and t plus 1. Am I right?
No, you are not right. So let me explain that. I did this in the very first week, I guess, but let me clarify this thing for you.
Okay.
So in dynamic models, we have two versions. Okay, continuous time and discrete time. Okay, these are two general classes. So this is continuous time. This is discrete time. Okay. Now in discrete time models, we either have a dynamical system okay, and then we study the steady states, stability, etc. Okay, or we have optimal control theory. In optimal control theory, this allows me to find the system, but now this system will be, so this system will be describing a path that is somehow optimal. Okay, all right. So the two parts are the same, but the difference is that if there is a decision maker that solves a dynamic optimization problem in continuous time, then this dynamical system will reflect this decision maker's choices. Okay. Now in the discrete time, the story is similar. Once again, we will have a system, and then we study the steady states, stability, etc. Okay, or we will have what we call dynamic programming. We're going to come to that. Okay. Once again, there will be an objective function here, a decision maker. That decision maker will solve some problems under some constraint, under some dynamic constraints. And at the end, we're going to still arrive at a dynamic system. And this will be optimal. Okay. This dynamical system will be describing an optimal path. Now, we did this, we are now doing that, and then we're gonna do this in the next weeks.
Okay, thank you.
All right? That's the idea. All right, let me give you one final example, and you, if I cannot solve it entirely, you work on this. All right. So, am I still sharing my screen? No. Okay. So in this example, we have growth and education. Okay. So the relationship is like this. Economic growth rate will depend on education in this way. Okay, so here theta and lambda are positive numbers and alpha is between 0 and 1. Okay, and education will also depend on growth, but in this way. Let's say where beta and psi greater than 0. As you see, this is a nonlinear dynamical system, right? You can assume that E0 and G0 are given. Okay, and they could be 0 as well. Okay, so the first equation tells you there is a dynamic of growth rate itself. So if you take this as constant, for instance, right? There's a dynamical system here. It's like this, right? But education enters this picture. If education is larger, then steady state growth is larger, right? If education is 0, it's like that. Okay. Now here, the second equation tells you that the movement of education depends on the growth rate. Why? Why do you think the movement of education would depend on the growth rate? And there's a positive relationship there. Well, it's very simple. There's of course a theory behind that. If you take my growth class, we're going to study such theories. But in one simple theory, the story goes like this. So if productivity growth is fast enough, then skill depreciation is large enough. So I don't want my skills to depreciate. So I increase my education spending, right? So if growth accelerates, I spend more on education. But for some cases, if growth is not important, if growth is small enough, if G is small enough, I do not spend any resources on education, so education is 0. All right. So there is a particular threshold value right here. If you look at this, there is this particular threshold. If G is less than psi divided by beta, then ET plus 1 equals 0, right? So there's this particular threshold. But this is an linear dynamical system, right? So you can study its dynamic properties. It's not that difficult. First, you're gonna find steady state, but now quickly realize that there could be more than one steady state, right? Why? Because in some cases, education could be zero, right? You must be seeing that very quickly. So I leave this as an exercise to you. I would have a couple more examples, but we managed our time poorly today. So I will give you as an exercise to you. I will give this to you as an exercise, and next week I will show you how to solve this one. If you want to prepare in advance for the next week, I'm going to look at Odette Gallor's text, Discrete Dynamical Systems, but you don't have to dive into the textbook. It's a text. Maybe you can start looking at chapter 3, chapter 4, chapter 5. So those are the only 3 chapters that we're gonna work on, but we are not gonna work on every single detail in these texts. Okay. So now we have 2 minutes. I can answer your questions. Anything? All right, everybody's happy then. So next week, we're going to continue with discrete dynamical systems. All right. Wednesdays,
Okay.
Wednesdays 1 p.m.
Okay.
All right. Bye bye then.
Good. See you.
Bye-bye.